everyone. Today I'll be showing you this presentation on polynomials, roller coasters, and derivatives. We will be screaming for second derivative today. In the roller coaster I have built in this presentation, I will be using many things featured in this bunch of images. This flat section right here, this slow curve to the end here, and this nearly straight down part are just a few to name some. This slide is just a simple outline of what I'm going to present today. Part 1, which is the first bullet point, is to explain what polynomials actually are. Part 2, the second to fifth bullet points, are to explain the requirements of my roller coaster and the design process. Part 3, the sixth and seventh bullet points, are to explain some interesting information about my roller coaster I built, an analysis of it, and some citations to sources I used. What are polynomials? A polynomial is a function that consists of multiple terms that each have a coefficient, variable, and exponent or power of that variable. Every single term has these two things. Now, you might be wondering, but Justin, what about that last term in all of them? They're all just numbers. Or that last term, it's just a number. Well, it actually does have both of those things. But you'd be right, it'd just be a number. Sort of. That term is called a constant, but it does still have a variable with a power. In this case, the variable is x, and you probably know that anything to the 0 power is 1, so that explains it. X to the 0 is 1, and 1 times with the coefficient, which is in front, is still the coefficient, which in this case was 4. And that explains the entirety of a polynomial. This slide shows you a couple examples of some graphs of the polynomial functions that I'll be using to construct my roller coaster. This top graph here has one arm. It has no turns. Now, you might be wondering, what are turns and why does this graph not have any? Well, a turn is when a line turns and goes in another direction. And maybe you're wondering the same about arms. Well, arms are just like flat parts. For example, the second one has 2 arms because it looks like it has 2 arms. Now, and since the first one, the graph I'm talking about, does not turn at any point, it's a straight line. This kind of graph is called a linear graph because it's a line like in linear. It has 2 terms as seen in the function shown on the left. You can also see these other examples such as this one in red and this one in blue. The name of the red graph is a quadratic graph, and the blue one is named a cubic graph with 3 arms and 2 turns. They all have more arms and more turns based on the power, the exponent of their variable, which in this case is x. As you can see, the green function has an x to the power of 1, the red an x to the power of 2, and the blue an x to the power of 3. This slide shows the design requirements for my roller coaster. My roller coaster will follow all of these 4 requirements. Requirement number 1. My roller coaster needs to have 4 relative maxima and minima. Basically, it just means it needs to have 4 hills. The second requirement is that the length of the ride is 25 seconds. Since it's designed for just family and casual fun, it shouldn't be too long. The third requirement is that the ride starts at 85 meters in altitude for a quick slope down in the beginning for great excitement and momentum to keep the ride rolling. The fourth and last requirement is just for fun, and it's that the ride has to go into a tunnel at the 2-second mark. To put it out there right now, I use Desmos to help and graph all the graphs in this presentation. This slide shows my design of my roller coaster. This intermediate stage is to match the design requirements. I used quintic polynomial A, quartic polynomials B and C, and a monomial equation D to make my roller coaster fit the design, and they are all shown below. I also used zeros and constants to adjust the curves and functions slightly to make them even more accurate. It took a lot of effort to make the line continuous, especially since all these are different functions with no relation to each other. If you don't get everything smooth and connected, when you take the derivative, it'll all be funky and weird, and no one wants to have their speed be 70 kilometers per hour and then suddenly be going backwards. You can see the functions on the bottom, below the graph. I had to zoom in quite a bit to get an exact value for all the constants and the zeros. And I want to mention it now. As you can see, the axes are labeled. The y-axis, which is the elevation, is in meters, and the x-axis, which is time, is in seconds. This slide shows the final design of my roller coaster. In this step, I determined the right domains for where to start and end each function to make a smooth transition between every function to make a continuous line which would eventually become my roller coaster. If you still don't know what a domain is basically telling where the function is, where to stop and end it, where to start it. Basically cut off the sides you don't need. As you can see down the bottom there, the equations from the intermediate design have been expanded into standard form using Symbolab. Polynomials A, B, C, and D have all been expanded to 5th order, 4th order, and exponential polynomials. This step is also helping to polish my design up a bit. I want to say again that the y-axis is in meters and the x-axis is in seconds because that's about to change. This slide shows the first derivative of my roller coaster. This was calculated using the 4 polynomial functions A, B, C, and D of the final design. The first derivative calculates the speed or velocity at every single point on my roller coaster ride. Mathematically, that just means that the first derivative calculates the slope at every point of my piecewise function. There's a quick exam definition of derivatives down at the bottom with an example. As you can see, all the 4 polynomial functions A, B, C, and D have just had their orders reduced by 1. just like the example. And just to show you that, on the final design page, function A, polynomial A, had an x to the 5 term in the beginning, but now it's been reduced to x to the 4. For the graph on this slide, instead of just meters for the y-axis, it's now meters per second, because now it's showing the speed or velocity at every point of the roller coaster ride, not just your elevation. That's pretty boring. Having 0 meters per second just means you aren't moving, right? It's very simple. You're moving 0 meters per second. That's represented by the 0 value on the y-axis of the graph. Having a large positive or negative y value just means that you're moving really fast, quickly, falling or climbing. But that isn't all, because falling or climbing, being fast or slow, doesn't actually determine how you feel. But this next one does. Now is when things get interesting. The first derivative showed the speed, yeah, but that isn't that great. You might think that that's what you feel, right? The speed. For example, maybe having a high speed means you feel fast. I mean, it makes sense, right? Fast speed, you feel fast. However, that's sadly not the case. If you stay the same speed, even at extreme speeds, maybe even really fast, you still feel like you aren't even moving if you just keep the same speed. I mean, inside the car, you're moving or whatever you're in. But when you look out the window, you don't actually feel fast. You just feel like, oh, I'm staying in the same place. However, what does calculate what you really feel? Second derivative. Mathematically, in this case, the second derivative calculates the acceleration. You've probably heard that before in science class. All the polynomials from the first derivative's orders got reduced by 1 again to get the second derivative, like the example and the first derivative. For example, function polynomial A from x to the 4 became x to the 3. As all the polynomials, they all got orders reduced by 1 to get the second derivative. That's shown at the bottom in the same format. As shown on this slide though, having a high second derivative means that at that point on the ride, you feel like your body's leaning forwards. Or maybe you feel like you need to get out of your seat, or it's pushing you out of your seat. Having a really high negative second derivative means you'll be pushed into your chair really far. Interestingly though, the second derivative is the slope of the first derivative, much like the first derivative is to the original final design function, polynomial function. For this graph, in the acceleration with the second derivative, just like the origin from the final design to the first derivative, we changed the y-axis from just meters to meters per second. Now it's meters per second one more time, also known as, or also said as, meters per second squared. This slide summarizes and compares the final design, the first derivative, and the second derivative of my roller coaster ride. For the 4 piecewise polynomial functions used to make my roller coaster, we have 4 peaks and 4 dips in this 25-second ride, more commonly known as 4 hills. By plotting the elevation, velocity, and acceleration polynomial equations together, we can see the most interesting points of this roller coaster. At times 2, 7.5, and 13.5 seconds, we can feel the most acceleration, which is the real feeling of going fast. At times 4, 6.5, 8.5, and 12 seconds, though, we feel zero acceleration, which makes us feel that we aren't even moving, even though the ride is clearly moving at a high speed. Now, on to the conclusions of this presentation. Number 1, polynomials are everywhere in our lives. From building roller coasters, or building smooth curved electronics, or building bridges, etc., polynomials are everywhere. Number 2, modeling roller coasters using polynomial functions is very effective and interesting. Number 3, derivatives are extremely useful in calculating speed and acceleration, which help planners improve upon their designs. Maybe they could add more bumps, long descents into tunnels, and much more to get the rider excited with all the feeling of going fast. Number 4, science and math are intertwined with our daily lives. For example, during shopping, you have to mathematically estimate what the total of your items may be before the checkout line to make sure you're not over budget. Or maybe during your video game, you need to estimate how far your enemy is to destroy them. Maybe another example is if you program a robot to hold an egg, you would have to determine how much power it should use to neither break the egg nor let it slide out. Number 5, computers help me a lot in creating my roller coaster. They help speed up the process of expanding and graphing many of these high power/order polynomials. Thank you very much for listening to my presentation. This page just has all the citations and references I used in this project. Yeah, just that. Well, let's address the elephant in the room. This absolute abomination of Lightning McQueen uses polynomials and derivatives for safety reasons. It's fun, and it's safe. I would again like to thank Symbol Lab and Desmos for speeding up the graphing and expansion of all the high-order polynomial functions. Also, according to my bib, this presentation is more credible than Kahoot. Interesting. If any of you are interested in fun projects like these, I'd be more than happy to help.